Hi Year 12. So on the first Monday back after half term, you would have had 2 math lessons with me. Now I don't know who's going to be in, I don't know who's still self-isolating. So what I decided to do is make a video where I basically just go through what we were going to go through in class, but I'm also going to go through your previous home learning. So I won't be going through that actually in the lesson. What I'll do is I'll tell anyone who's in on Monday that if they want to have a look at this, then obviously I'll direct them to this video. So anyway, to get started, these were your homework questions. So there was question 5, question 6, and question 7. I'm going to go through them now. There will be timestamps in the description. So if you just want to skip ahead to what we are doing in the lesson, please look in the description and click ahead. Okay, so number 5. A curve has equation y equals 2x cubed take away 6x. And then question 1 says, find the points where the curve crosses the x-axis. Okay, so for number 1, so we cross the x-axis. Now, if you think about the coordinates that are on the x-axis, they're like 1, 0, 2, 0, 3, 0, 4, 0, lots and lots of different possibilities, but they all have the y coordinate equaling 0. So that means we have to set y equals 0. So we'll have 2x cubed minus 6x equals 0. So this is the equation that we want to solve. So let's have a look. What do we have? Well, we can divide this through by 2 both sides. So if I divide the left hand side by 2, I'll get x cubed minus 3x. And if I divide 0 by 2, I get 0. And then I want to go ahead and factorize this. So this is x lots of something. So this is x squared minus 3. And this part here actually can be factorized, just not very nicely. So this part is actually x minus root 3, x plus root 3. So that's something to be mindful of, that back at GCSE you had the difference of 2 squares, and obviously it's nicer if that number is take away and it's a square number, but it doesn't have to be. It can be take away anything, and it'll factor as x minus the root of that thing, x plus the root of that thing, and then this equals 0. So there are actually 3 values of x that satisfy this. There's x is 0, so x could be 0, the whole thing would be 0, so that would be x is 0. Or x is the positive square root of 3, or x is the square root of 3, or x is minus the square root of 3, so x is minus root 3. And it wants the points, so it's not enough just to say what x is, you have to say what y is going to be. So that's 0, 0, and of course it's not a lot of extra work, is it, because the y number is all 0 on the x-axis. So we've got those 3 coordinates there. So that's where this curve crosses the x-axis. Now it's very important to note something here. Whenever you divide both sides of an equation by something, you always want to have in the back of your mind that you cannot divide by 0. So whenever you're dividing by something, you want to ask the question, well, can that thing be 0? So when I decide to divide both sides by 2, I mean, it's a very quick check. Can 2 equal 0? Well, no, it can't. Right, so fine then. You're allowed to divide by it. What you could accidentally do, and this is so one person accidentally got rid of the x equals 0 solution. That's because they divided through by x both sides. So they were left with just x squared minus 3 equals 0. Now, that is a very common mistake. And what you can do to avoid that is say, look, could x be 0? well, on the face of it, yes, let's check. Does x equals 0 solve the equation? So you do 2 lots of 0 cubed and take away 6 lots of 0, and you'd say, oh, right, okay, so x could be 0 then. Right, so I shouldn't divide by it then. That's one thing to sort of always try to keep in the back of your mind. Okay, if it turned out that x is 0 doesn't actually solve the equation, then you could divide by it. You wouldn't be getting rid of anything by doing that. So anyway, let's move on. So part 2. So we want dy by dx. So let me write the little equation again. So it's y equals 2x cubed minus 6x, and we want dy by dx. So that's going to be 6x squared minus 6. And then it says, hence find the stationary points on the curve. So this has to equal 0 for a stationary point. So if you watched either of the previous 2 videos, you should be, well accustomed to seeing this kind of thing be written. Okay, you differentiate once and you set it equal to 0, and then you write at a stationary point. Okay, it's not just that dy by dx just automatically equals 0. Okay, it can equal lots of different things, but if we're looking for a stationary point, we're looking for when it equals 0. And so this is now a situation where, okay, we're now going to solve this. So I'm going to divide both sides by 6. 6 can't equal 0, so I'm allowed to divide both sides by 6. So that's x squared minus 1 is 0, and then you've got 2 options, right? You could add 1 to both sides and square roots. So, option 1 would be x squared is 1, so x is plus or minus 1, the square root of 1. I guess technically it's like that, and then, okay, well, that's plus or minus 1. Another alternative is to actually factorize this as the difference of 2 squares. And so there's x equals 1 or x equals minus 1. So either way, you get 2 possible x values. So we want minus 1, and then we have to work out what the value is at minus 1, and then we have 1, and we have to work out what the value is at 1. Now remember, we're not going to be plugging that back into dy by dx, because if we plug either of these into dy by dx, and we're going to get 0, we're actually wanting to know what the actual coordinate is on the graph. So that's given to us by this here. So I need to do minus 1 cubed, which is minus 1, times 2, which is minus 2. 6 times minus 1 is minus 6, so I'll be on minus 2, and I'll be taking away minus 6, so that'll go up to 4. And then here I'll have put 1 in, so that's 2, take away 6 is minus 4. So we have 2 stationary points, minus 1, 4, and 1, minus 4. Okay, and then part 3 asks us to basically do the second derivative test. So I might as well kind of squeeze that in here. I'll change colour of pen just to make it clear what I'm doing. So this is part 3. So we're going to do d2y by dx squared. It's basically asking us to do the second derivative test. So that is just 12x. And I'm just going to, I would set this out more neatly if I was actually handing in a piece of homework. But if I'm going to take what I've written here and continue it in blue. So d2y by dx squared when x is minus 1, that would give me minus 12. So therefore this one's a maximum. And d2y by dx squared when x is 1 gives me 12. So therefore that one is a minimum. So I've categorized these as a maximum and as a minimum point. Right, and then the last question says sketch the curve. So actually I have quite a lot of unused space over here. So let me do that. So when it says sketch the curve, it's not so bothered about every coordinate being spot on. It wants the correct overall shape, and it wants points of intersection with the axes, so that's both the x and the y axis, kind of labeled, and it wants stationary points kind of illustrated as well. So one of the first thing to do is to do we well, you could do either axis first, actually. If you want to say where does it intersect the y-axis, so that's when x is 0. So if you make x equal 0, of course you get 0, 0. So that's one of the points where it also intersects the x-axis, right? Because one of those coordinates was 0, 0. So let's go back and see. One of them was 0, 0. Then we've got root 3, 0 and minus root 3, 0. So root 3 is about 1.7. So if there's about 1, so if I make this be 1, and maybe that'll be 2, it's going to go there, and then here'll be minus 1 and minus 2, and then there'll be 1 here. And then what you've got is minus root 3 there and root 3 there. And then I've put these minus 1 and 1 in. I mean, really, to be honest with you, I don't really need to write the minus 2. That's kind of just getting in the way a bit. Anyway, so the reason I need the minus 1 and the 1 is not just for scale, but also because that's where there are some stationary points, right? There is a maximum at minus 1, 4. So you'd kind of... It's just a sketch at the end of the day, so you're not worried about it being absolutely perfect. But you know there's a stationary point here at minus 1, 4, and you know there's a stationary point here at 1, minus 4. And you can say something more about it as well. You know that this one here that I've just done is a minimum, so it's going to be drawn as the bottom of a valley. And this one here is a maximum, because it's what we established over there, so it's going to be drawn as the top of a hill. And then with some basic GCSE knowledge about the shape of a cubic, you know it's going to come up from down here, go through that coordinate there on the x-axis, and then go through there. Of course, it's not the easiest thing in the world to do on the computer here, but hopefully you get the idea. That is really terrible. We're going to persevere though. Yeah, this is absolutely rubbish. That is really, 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 really terrible. Okay, so I'm going to cheat slightly and go show you what it looks like on Desmos. Very difficult to use this this thing here. Anyway, let's not worry too much about that. Of course, you can be neater on a bit of paper. Here is what it's supposed to look like. So we're just going to pretend that I drew this. All right. So so we pretend I've drawn that. We're just gonna totally pretend. So this is minus 1, 4, and this is the 1, minus 4. There's the, so it's made a reappearance. It doesn't want me to forget about it. There we go. Okay, it's gone now. Good. Right, and then here we've got minus root 3, and here we've got root 3, and of course there's the origin. So anyway, what's the point? Well, the idea, of course, is that to draw a cubic without having to compute loads and loads of different points, in the same way that back at GCSE you would be told, you know, sketch a parabola, you know, here's a quadratic, can you just do the general shape? So you just work out where does it cross the x-axis, where does it cross the y-axis, and identify the minimum point, which back then you would have done either by going halfway between the roots. So that was one option, and another option was to complete the square, and that would be you working out the vertex of the graph. So it's just the same really, except now you can do it with more complicated functions, because you can it's the same idea. You work out where it crosses the axes, and you work out where you have stationary points. And then you can do a better sketch than my original one if you've got paper in front of you. But of course you can also look at Desmos to see what it should look like. Right, hopefully that's been helpful. Okay, question 6. So, find the stationary points of this here and then determine the nature of each of them. So that's going to be a second derivative test, right? So what I'm going to do is straight away write this, well, using indices. because then it's going to be a lot easier to differentiate. So I just have to be very careful, basically. So times by the power and knock 1 off the power, times by the power and knock 1 off the power, times by the power and knock 1 off the power. And I will also, because I'm going to have to do the second derivative test, I'm going to do d2y by dx squared as well. So we've got to differentiate again. So times by the power, knock 1 off the power, times by the power, knock 1 off the power, and finally times by the power, knock 1 off the power. Now I'm actually going to tidy both of these up. So I've got minus 1 over x minus 2 over x cubed plus 3 over x to the 4. And I'm actually going to write this with a common denominator. The reason I'm going to do that is because I know I'm going to be setting it equal to 0. So I'm going to times top and bottom by x cubed times top and bottom by x. There has been a mistake. So times by the power and knock 1 off the power makes that a 2. And times by the power and knock 1 off the power. Okay, there we go. So I think I'm actually going to leave that in because you know, it's good to see that everyone can make a mistake, right? So let me just double check. So that looks right now. Okay, continuing. We're going to times top and bottom by x squared. We're going to times top and bottom by x, and then our common denominator will be x to the power of 4. So this will be a minus an x squared minus a 2x and then plus a 3. So what I've done is times top and bottom by x squared, so it's minus x squared on the top, times top and bottom by x, so now it's minus 2x on the top, and then this has stayed the same. And then I don't think I necessarily need to do it with this, just because I'm just going to use a calculator for this part. But I did really need to do it for this, just because I'm going to be setting it equal to 0. So dy by dx is 0 at a stationary point. So therefore, I'm actually solving this equation here. Minus x squared minus 2x plus 3 all over x to the 4 is 0. Now, if you have a fraction equaling 0, then the numerator has to be 0. An alternative way of thinking about this is I'm just going to times both sides by x to the power of 4, right? On this side, I'll be left with the numerator, and on this side, I'm going to have 0 times x to the 4, which is, of course, still just 0. So it's actually enough to just solve this. Minus x squared minus 2x plus 3 is 0. And because I don't like solving negative quadratics, I'm now going to times everything by minus 1. So that's actually x squared plus 2x minus 3 equals 0. So let me continue this here. So that factorizes as what? X minus 1, x plus 3 equals 0. So 3 times minus 1 is minus 3, and 3 take away 1 is 2. So you've either got x is 1 or x is minus 3. So let's keep going. We have got, let me just take some bit to screenshot, a few screenshots for the, because we're running out of room. So we've got the actual y. We have got what dy by dx is equal to. And we've got what d2y by dx squared is equal to. And we know what our stationary points were. So I guess we've got 2 jobs left to do. We're going to make x be 1 in y to work out what the actual coordinate is. And we're going to put it into d2y by dx squared to determine whether or not, well, what sort of stationary point it is. And then we're going to do that again for -3 as well. So there's not really any set order to this. You just have to kind of do it. So let's do 1 and then plug it into here. Well, that's not so bad. That this is 1 plus 1 is 2. Take away 1 is 1. So 1, 1. And we've also got -3, and if we use the calculator for this one, because it's obviously not as nice as it, we've got 1 over -3 plus 1 over -3 squared. Minus 1 over -3 cubed. So -5 over 27. So I would just leave that as -5 over 27. Okay, so these are our two stationary points. So like we've actually got that part done. The next part is to categorize them. So I'm going to use d2y by dx squared for this. So I'm going to do, well, what have I got? d2y by dx squared when x is 1 equals. I'll also have d2y by dx squared when x is -3. So back on the calculator then. Well, all of these x's when x is 1, they're all just powers of 1. So I can do that. 2 plus 6 is 8, take away 12 is -4. So since that's -4, this one's a maximum. And most likely the other one's now going to be a minimum. But, you must check. So one thing we can do is we can put -3 in. We can click M+. So now whenever I use M, it's -3. So that's one of the good things about that button. So I'm going to do 2m to the -3 plus 6m to the -4 minus 12m to the -5, and I get 4 over 81. And since that's positive, it's a minimum. So let me just double check. Okay, so that's that one done. That's it. Okay, finally number 7. We've got x and y are real numbers. So all that means, by the way, is they just can be any decimal, positive or negative, including rational and irrational numbers. They're basically just all the possible numbers along the x-axis, all the possible numbers on the y-axis, just any number on a number line, essentially. That's what real numbers are. So anyway, so they're just any old number. And what are they? Well, they satisfy that 2x plus y is 100. And we want to know what the maximum value of the product of the two numbers is. So the thing I would naturally do here is say, look, we're wanting to maximize the product. So let's give the product a name. So P is obviously x, is just xy. Now I would love to be able to do, differentiate this and set it equal to 0. However, the problem is this is a function of two variables, and so we can't differentiate that. Well, not yet anyway. But we don't have to in this form. We actually have something which is very useful, because y is actually just 100 minus 2x. So that's x lots of 100 minus 2x, which is 100x minus 2x squared. And it's like, oh, brill. Well, now I can differentiate it and set it equal to 0. So dp by dx will be 100 minus 4x, and that'll be 0 at a stationary point. There will be a tiny bit of work to do to show it's a maximum, remember. We don't get that it's a maximum straight away. We have to do the second derivative and show that that is going to be negative. Well, we could do that straight away, actually. Look what happens. It doesn't even matter what x is. The second derivative is minus 4, no matter what. Now, since that's less than 0, it's going to be a maximum. So, great. In particular, at whatever x value solves this, the second derivative is negative 4, so it's a maximum there. Anyway, 100 minus 4x is 0, tells you that 4x is 100, tells you that x is 25, and it would be great to know what, of course, y is, and therefore what the product is. So I've basically just got to do, the product is 25 lots of 100 minus 2 lots of 25. So I'm just substituting into this here, okay? So that is equal to 25 times 100 minus 2 lots of 25. Okay, so this is just 50 25s, okay. So we didn't really need a calculator for that, but you know, we're allowed to use one. So this is 1,250. And we know it's a maximum value of p, where we are literally trying to, this was a function p in terms of x. Now, whatever this looks like, I mean, it's like an upside down quadratic, isn't it? So it does have a maximum value. And it turns out that it attains its maximum value when x is 25, and the maximum value that it gets is 1,250. Right, so that's that done. Okay, so on to the actual lesson. So if you are in on Monday, the first thing you'll see is this bell task. So of course I would say, you know, hello, how is everyone? But of course it's a video, so you can't easily reply to me. But anyway, whatever. Here's the question. So if y is, and then it's some number times x to the n plus some number times x, and then it tells you what dy by dx is, without any a's or b's or n's, it then says, okay, you know, given that information, can you work out what a, b, and n must be? So what I would ask you to do is pause the video, write down that form of y, write down that form of dy by dx, and then see if you could work out how to answer this. So, you know, you can have as long as you like, right? I might even, you know, encourage you to have a go, and if you really, really struggle, then you could email me even before resuming the video. So what I'm going to do is I'm going to like suggest that you pause and have a go. Then what I'll do is I'll give a couple of hints, and then I'll we'll pause again, and then what I'll do is I'll go through the question. Okay, right. So pause, try. Okay, so I'm assuming you've had a go. You just have to sit and listen to these hints if you've already answered it. Otherwise, here are the hints, right? Differentiate this. So actually, tell me what dy by dx is, and it'll have a bunch of a's, x's, n's. It'll have a b there as well. If you differentiate that and then compare it to this, you should be able to, especially after using your knowledge of index laws, you should be able to figure out what the numbers a, b, and n are. Okay, you could even set it up as like some simultaneous equations, actually, some not even particularly difficult simultaneous equations. Right, have another go, and then and pause, and have another go, and then come back, and I'm going to go through it now. Okay, so following my own advice, I'm going to differentiate this. So dy by dx is, so you times by the power and knock 1 off the power, plus, and then bx would just differentiate to b. And this is supposed to equal, let me write it, you see how this part here has the x in it, and this is just a number? You see how that's just a number? It means b is going to be that 1, right? B is just 1. So let me write it like the other way around. Minus 1 over cube root of x to the 4 plus 1. And so next job I might do is rewrite this like just using indices. No cube root symbol, no fraction. The reason is then I'll be able to compare it to this. Okay, so this is the idea. So this is minus, and then this is x to the 4/3, but it's really x to the minus 4/3. So x to the minus 4/3 plus 1. So it's a minus 4/3. It's minus because it's a reciprocal. And then it's the power 4, but then it's cube rooted, so that's 4/3. And so what you actually end up with is, well, the little power n minus 1 is minus 4/3. Well, this is not so difficult to work out what n has to be. You also know that the thing in front of that, the an, has to be minus 1. And we also know that the b has to just equal 1. So actually b equaling 1 is kind of like, well, we already done. B was 1. Let's do n minus 1 is minus 4/3. I guess that tells us that n is minus 1/3. Right? Because if you add 1 to minus 4/3, you're adding on 3/3, so you land on minus 1/3. And then we now know that n is minus 1/3. So times both sides by minus 3, and you would have a is 3. Right? If you do 3 times minus 1/3, you get the minus 1 that we want. Okay, so it turns out that a was 3, b was 1, and n was minus 1/3. Now you could even check this out, right? If you do 3x to the minus 1/3 plus 1x, which is just x, and differentiate that, well, you'll times by the power, so that's minus 1 x to the minus 4/3, and then just plus 1. So the 1 has been written the other side. It's been like swapped around to kind of try to trick you out. And then of course that as you know, a reciprocal and written with a cube root is 1 over the cube root of x to the 4. Okay, that's what that is. Okay, so that was the bell task. Then you would be greeted with the starter. So the starter question, again, you're going to be given some time to do this. One of the reasons that these bell tasks and starters maybe take a little bit longer is because, of course, you have 2 lessons and there's not going to be a bell task and starter for the second lesson, okay? So it's quite all right for this to be taking a little bit of extra time. But anyway, it gives you an f of x, it's x cubed plus x, and it wants you to work out what f of 1 plus h is. So that's your first job, and it tells you also how it wants you to write your answer. So there'll be something plus something h plus something h squared plus something h cubed, and you have to work out what the a, the b, the c, and the d numbers are. Okay, so that's part A, and then part B says, okay, well, we've got a curve that has that f of x as the y equals, well, it's y equals x cubed plus x, so it's going to, you know, have some cubic shape, right? And it passes through, well, it tells you what one of the points is, 1, 2. So if you put 1 in here, you'll see that the output is indeed 2, so good, that works. And it also tells you what happens when you put in 1 plus h. Okay, you get 1 plus h cubed plus, and then obviously 1 plus h. And actually, this thing has been written like this only so it doesn't give away the answer to part A, right? If you expand all of this out, this would be the answer to part A, right? And then, okay, it says write down what the gradient between P and Q is. So these are like two actual points for some distance h away. H could be a big number, h could be a small number. And then it says, right, now use an appropriate limit to actually find f dash of 1. So it actually wants to know what is the gradient at 1 exactly. So of course you'll need to use an appropriate limit. So pause and have a go, then come back and listen to some hints if you need to, and then I'll pause again and then I'll go through it. Okay, so pause and have a go. Right, so the hints are, well, the first one, there's not really any hints other than to just do it. You're just going to have to sit and do it. The second one, the gradient between 2 points is the difference in the y numbers, take away the difference in the x numbers. Sorry, not to take away. This is a terrible hint. It's the difference in the y's over the difference in the x's. And then the limit would be to take the limit as h goes to 0. Right, pause and have a go, and then when you come back I'll go through the answer. Right, here we go, here's the answer. So you could either do, 1 plus h, 1 plus h, 1 plus h, and expand it all out using, like 2 grid methods, or like FOIL, however you want to do it. You can also just do, it's 1 cubed plus 3 lots of 1 squared lots of h plus 3 lots of 1 lot of h squared plus h cubed plus 1 plus h. So I'm just doing like a binomial expansion. So this is 1 plus 3h plus 3h squared plus h cubed plus 1 plus h. So this equals, and then of course this is h, once it written this way around, doesn't it? So it's 2 plus 4h plus 3h squared plus h cubed. Right, so A was 2, B was 4, C was 3, and D was 1. Right, so this is actually what this thing equals, isn't it? It's 2 plus 4h plus 3h squared plus h cubed. So this gradient then is the difference in the y's. So it's 2 plus 4h plus 3h squared plus h cubed, take away 2. Right, it's this take away this 2 over the difference in the x's, which is of course just 1 plus h take away 1. So when you simplify this, you get 4h plus 3h squared plus h cubed all over h, which, okay, we can simplify again. It's 4 plus 3h plus h squared. Okay, so that's what that answer is. It's 4 plus 3h plus h squared. And then the appropriate limit would be to take the limit as h goes to 0 of this. Which is just 4. Okay, so the gradient at the point when x is 1 is 4. Now, let's just kind of double check using our, our knowledge that we've gained now. Let's differentiate this. So f dashed would be 3x squared plus 1. And indeed, if you make x be 1, you get 1 squared is 1 times 3 is 3, and 3 add 1 is 4. Okay, so there you go. It all works out. Right, hopefully that was all right. We would be going to page 94. So you need to be on page 94 in your book. And what I'm going to do is just kind of have this open myself. Right. So we've got section 4.3, rates of change. Now, you've actually done section 4.4 and 4.5, and now we're coming back to do 4.3. So this was for two reasons. One is the actual questions that are asked. They're a little bit easier than the ones that you did just before half term, and I thought, it's nice to come back after people. It was probably a good idea anyway. To come back after half term and not be greeted with something really, really, brand new and awful and really difficult. But also because this is also made easier by what you've already done. So it's kind of like two good reasons to have kind of left it. So if you read what it says in the book, it says, okay, so when y is a function of x, the gradient of a graph of y against x tells you how the y measurement is changing per unit x measurement. So that's just a kind of a way of describing what a gradient is. And then it says, okay, so that's the rate of change of y with respect to x, and that can be written as dy by dx. It's just the gradient. It's like, and it's a lot easier to think about straight line graphs as well. For, if I think about y equals 4x add 3, if there's a little change in x, what's the little change? What's the corresponding change in y? Well, it's 4 times whatever it was. The 4 times the little change in x. That gradient being 4 just tells you that if you change x by 1, you change y by 4. Right. So a little change in x corresponds to if in that situation a 4 times change in y. That's what a gradient is. Has lots of ways of interpreting it, a lot of ways. And so in section 4.3 they talk about distance time graphs and velocity time graphs. So these are things from GCSE. So the x-axis is really the t-axis or time, and then if it's a distance time graph, obviously you're as time goes on, you're plotting how far away are you, and then as you come back, it comes back down and things like that. And then the velocity time graph is, again, as time changes, the graph goes up if you speed up, and the graph comes down if you slow down. And if the graph is ever at 0 in that situation, then you're just not moving. So anyway, if you have a distance time graph and you differentiate it, you get the velocity. So the derivative of distance with respect to time, which it's like distance over time, which is speed. If you do dr by dt, that is velocity. So all of this is kind of summarized on page 94. Of course, if you're actually in the lesson, we would be having a conversation about this. So it's kind of hard to judge what you already know and what you're not sure of. And then anyway, if you then differentiate that again, or if you start with velocity, if you differentiate velocity, you get acceleration. So that's basically kind of the key points on this page 94 are obviously very, very important. And then, okay, well, it tells you about the second derivative, but you already know about the second derivative. And then if you turn the page to page 95, it just basically tells you if dy by dx at a particular point is positive, then you are increasing. You are an increasing graph. And that just means the gradient's positive, which means it's going uphill. It's increasing. It's starting from something smaller to then ending up at something bigger. And if dy by dx is less than 0, then that means the gradient is negative. It's going downhill. It's decreasing. And of course, you already know that if at any point you have dy by dx equals 0, then it's not increasing or decreasing there. It is stationary. So that's the definition of a stationary point. So this very much ties in with things that we've already talked about. And so what we would be doing for like the rest of period 1, and maybe some of period 2, because it depends on how long the Bell Task and Starter took, is you would have a go at exercise 4.3a. So when I look at exercise 4.3a, you are just differentiating and substituting in a value. That's question 1. For question 2, it's asking you to do d2y by dx squared. For question 3, it wants you to work out where each curve is stationary, where each curve is increasing, and where each curve is decreasing. So there you're either setting dy by dx equals 0, or you've got dy by dx is greater than 0, or you've got dy by dx is less than 0. So that actually kind of ties in with solving inequalities, which is something you would have done at GCSE. So I really think, that would have then been an opportunity to kind of sit and do some work. Right, and then we would have gone on to page, so this would have probably now been the second lesson, we'd have been on page 97, and I've got example 3 on page 97 and example 4 on page 98, and then I would be asking you to do exercise 4.3b. So if I talk about example 3 first of all, so it says we've got a conical vat which is filled with water. So this is just a cone that's full of water, and the volume in the vat at time t seconds is v. So v is actually a function of t. So this is the first thing to take note of. It's actually, the volume is a function of time. And okay, and it even says that in the second sentence. So I've preempted what it says in the second sentence. So v is a function of t. So we would write v of t, such that the volume at time t is found by multiplying the cube of t by 50 pi. So we've got the volume at time t is 50 pi t cubed. That's just about fit in there next to the camera there. Now, that's actually what it says here, by the way. And so what this means is okay, well, when it starts, how full is it? Okay, well, when t is 0, that's when it starts. Starts at when t is 0, so it starts with no water in it. And then it starts to fill up. After 1 second, it's got 50 pi. Oh, it doesn't tell us what any units are. Oh, okay, a V is measured in milliliters. So it's got 50 pi, which is about 150-ish. Not particularly precise, but it's about 150 milliliters, right? So you can actually plot this graph. You can see how full it is after a certain length of time. You can also tell that obviously it's as time goes by, it fills up faster and faster and faster, because t cubed is, gets faster and faster. So the first question just says work out v dash to t. So it means differentiate it. That then when you differentiate this, that's the answer you get. And so that would be milliliters per second, right? Because this is like dv by dt. This is milliliters per second. And that actually itself depends on t, because it's not increasing linearly, right? It is itself speeding up. As every second goes by, it increases the rate at which water is poured into it. And then it says, okay, calculate the rate at which the vat is filling with water after 3 seconds. So you're just going to put v dash to 3. And, okay, and then it asks you to, well, it doesn't actually ask you to do anything other than write 1,350 pi. But it then goes ahead and rounds it, and then that's milliliters per second. So anyway, that's that one. So as I say, if you are at home and not able to ask me for help in the lesson, and you're confused about any of this, please send me an email. Okay, example 4. An object is thrown into the air, and this is a function of its height after t seconds. So it starts, so it tells you, okay, h is 1 plus 30t minus 5t squared, where h is its height in meters. So where does it start in terms of how tall is it when it starts? Well, it starts when t is 0, so it starts 1 meter off the ground, which I guess makes some sense if you're about to throw something, that the object is about a meter off the ground. And then I guess what happens is it goes up and then comes back down. In fact, what we could do even is I could show you what this looks like on Desmos, because this is probably something I would do in class. So 1 plus 30, I guess it's x for Desmos, so 5x squared. It gets thrown really, really high in the air. It's kind of crazy. So it's probably not a person who's thrown it. But anyway. So I'm going to show you what this looks like so you can have a bit of context. Okay, so it starts here, a meter off the ground, and then it's thrown up, and this is the trajectory it takes. So this person has thrown this really, really high, really high. It's probably not been thrown by a person, to be honest, to reach this tall. But anyway, and then it comes back down to Earth. So a motion under gravity, by the way, is very typically modeled using a parabola, so using a quadratic function. It's not quite right for real life, because you would have some air resistance, like some wind, so it wouldn't follow this exact trajectory. But a lot of the time, it's a really good approximation of anything is kicked. So if a goalkeeper takes a goal kick and then the ball gets obviously kicked, it follows the shape of a parabola, except obviously not quite because of added complications such as wind resistance. And if it's a ball as well, there'll be spin on the ball as well. But a very, very simple model for motion under gravity is using a parabola. So anyway, that's what that looks like. So that's that. Write down an expression for the rate at which the object is climbing in meters per second. So we're just going to do dh by dt, because it's saying it's a rate, which means it's a derivative with respect to t. So this is something that you should maybe make a note of. Whenever you're asked for a rate of something, you're doing d by dt of that thing, right? It's like a rate of something is something per second, or something per hour, or something per unit of time. So it actually says, look, it's in meters per second. So this was originally in meters. We now want something that's in meters per second, so we're going to differentiate it. So that's that answer there. Then it says, work out when the object is rising and when the object is falling. So it's going to be rising when dh by dt is positive, right? Because then it's an increasing function. So you solve this greater than 0, and I guess this is what you get. So t is less than, so for anything up to and including 3 seconds, and actually if you remember what the graph looked like, that was what it looked like, right? There's the 3 seconds there, and it was rising all the way to the top, and then it starts to fall. Right, it got to 3 seconds in, and then it started to fall. And then when the object is falling, it's when t is greater than 3 seconds. The object is actually completely stationary for like a split second in the air as it's reached the very top, and then it starts to fall. And that happens at exactly t equals 3 seconds. And then it says, after how many seconds does the object reach its maximum height? Well, that's actually quite an easy question. So this is all geared up to, I thought it was going to be a bit harder than this. After how many seconds does the object reach its maximum height? So it reaches its maximum, well, you'd have a stationary point. So you'd want to differentiate and actually set equal to 0. And of course, you already know that the answer is 3 seconds to that. There is a little bit more to it, because you'd need to do d2h by dt squared, which the book kind of neglects, because you want to show that it's actually a maximum. But the point is that that's just minus 10, isn't it? So that's definitely a maximum then. But of course we know it's a maximum as well just by looking. So then anyway, you would do exercise 4.3b, and basically it's just a lot of very similar questions that we've already looked at, but the function isn't just like y is a function of x. It doesn't just give you this function. It's like a formula for something in particular that's within the context of the question, and you kind of go from there. So you would have a go, obviously, at exercise 4.3b, and then what I would want you to do is have done exercise 4.3a and 4.3b by the time I then saw you on Thursday. And then, of course, any problems you can email, or you can come and see me, anything like that, and then we would go from there. Because on what we're going to do on Thursday is there's going to be like I'm going to do a lesson where I kind of just summarize all the stuff to do with differentiation, because we're going to need to very quickly turn our attention to integration, which is the next part of this chapter 4. So anyway, I'm going to end the video there. So yeah, I want you to do 4.3a and 4.3b for Thursday. It's not a homework that you necessarily need to, so you're not submitting this for me to mark, because you can just look at the answers in the back, but I need to see that you've done them, and I need to make sure that you know how to do them. So any questions, any difficulties, you let me know, okay? Other than that, if you are at home and not in on Monday, well, I hope everything's all right. If I can support you at all with anything to do with your maths, I've said it once, I've said it twice, I've probably said it about 100 times at this point. Please just send me an email, and I will get back to you as quickly as I can. But other than that, hopefully see you soon. Take care, and yeah, you've got some maths to keep you busy. Right, thanks very much. I'll see you in the next one.